Hello everyone. So we'll discuss about the artificial recharge techniques and the designs. So in the previous video we have discussed about the basics of artificial recharge techniques and the different kind of studies that are being covered for planning an artificial recharge. Now we will discuss about the techniques and the designs. So a wide spectrum of techniques are in application for recharging the groundwater reservoir. Similarly, to the variations in hydrological framework, the artificial recharge techniques are again wide in number. We will discuss some of the broadly classified techniques. They are like the direct surface technique, the direct subsurface technique, and combination of both surface and subsurface techniques, and indirect techniques. So when it comes to the direct surface techniques, that means these techniques are followed on the surface directly. They are flooding, basins or percolation tanks construction, stream augmentation, ditch and furrow system, and over irrigation. These are the direct surface techniques. And when it comes to the direct subsurface techniques, these are done in the subsurface. They include injection wells or construction of recharge wells, and then construction of recharge pits and shafts, dug well recharge, the borehole flooding, natural openings, cavity filling also. And sometimes we have the combination of both surface and subsurface techniques. This includes basin or percolation tanks with pit shaft or well construction. Apart from these, you have some indirect techniques also, in which the induced recharge from surface water sources and also the modification of the aquifer. Besides these, the groundwater conservation structures like the groundwater dams, subsurface dikes, or locally called as bandaras, are quite prevalent to arrest the subsurface flow. Similarly, in hard rock areas, the rock fracturing techniques include sectional blasting of boreholes with the suitable techniques has been applied. This is to interconnect the fractures and increase the recharge. Cement sealing of fractures, though specially constructed borewells are being utilized in most of the parts of India to conserve the subsurface flow and augment borewell yield. So this is what we have discussed regarding the artificial recharge techniques. So we will go for a discussion of artificial recharge structures. So in the structures we will discuss about the ditch and furrow method. If you take an area with irregular topography, shallow or flat bottom, and is closely spaced ditches or furrows, they provide maximum water contact area for recharge water from source stream or canals. This technique requires less soil preparation than the recharge basins and is less sensitive to silting. So generally 3 patterns of ditch and furrow system are adopted. The first is lateral ditch pattern, second is dendritic pattern, third is contour pattern. In the lateral ditch pattern, the water from stream is divided into feeder canal or ditch, from which smaller ditches are made at right angles. The rate of flow of water from the feeder canal to these ditches is controlled by gate valves. The furrow depth is kept accordingly to the topography and also with the aim that maximum wetted surface is available along with the maintenance of uniform velocity. The excess water is again routed to the mainstream through a return canal along with residual silt. This is a part of lateral ditch pattern. In the dendritic pattern, the water from the stream can be diverted from the main canal to a series of smaller ditches spread in a dendritic pattern. The bifurcation of the ditches continues until practically all the water is infiltrated in the ground. So this is about the dendritic pattern. Then we will go for the contour pattern. The ditches are excavated following the ground surface contour of a particular area. When the ditch comes close to the stream, a switch bank is made, and thus the ditch is made to meander back and forth to traverse the spread area repeatably. At the lowest point down the stream, the ditch again joins the main stream, thus returning the excess water into it. So these are the patterns, and if you go for the characteristics and designs of a site, then what we should consider. This method is adaptable for irregular terrain. The water contact area exceeds 10% of the total recharge. Ditches should have slope to maintain flow velocity and a minimum deposition of sediments. The ditches also should be shallow, flat bottomed and closely spaced to obtain maximum water contact area. In general, the width would be 0.3 to 1.8 meters. And finally, a collecting ditch to convey the excess water back to the main stream channel should be provided. These are the guidelines and the characteristics to be taken when we are following the ditch and furrow method for the artificial recharge structures. The same way, when we discuss about the percolation tanks or the spreading basins, we can discuss more. These are the most prevalent structures in India as a measure to recharge the groundwater reservoir both in alluvial as well as in the hard rock formations. The efficiency and the feasibility of these structures is more in hard rock formation where the rocks are highly fractured and weathered. So if you can see the typical designs here, the percolation tanks have feasible in mountain fronts occupied by the talus scree deposits. These are found in more effective mountain areas. The percolation tanks can also be constructed in the zones. The percolation tanks with wells and shafts, percolation tanks are also constructed to recharge the deeper aquifers where shallow or the superficial formations are highly impermeable or sometimes clayey with certain modification. The recharge wells with the filter are constructed in the percolation tanks, and the stored water is seen here. Now let us discuss about the important aspects of percolation tanks. A detailed analysis of rainfall pattern, number of rainy days, dry spells and evaporation rate, and detailed hydrogeological studies to demarcate the suitable percolation tank sites. And the other aspect is, if you take peninsular India with the semi-arid climate, the storage capacity of percolation tanks can be designed such that the water will percolate into the ground, into the reservoir by January, since the evaporation losses would be highly subsequent. So the percolation tanks be normally constructed on second to third order stream. Since the catchment, so also the submergence area would be smaller. The submergence area should be in uncultivatable land as far as possible. Percolation tanks be located on highly fractured and weather drops for speedy recharge. If you take an example of alluvium, the boundary formations are ideal for locating the percolation tanks. The aquifer to be recharged should have sufficient thickness of permeable vadose zone to accommodate recharge. The benefited area should have sufficient number of wells and cultivatable land to develop the recharge water. And also detailed hydrological studies for runoff assessment be done, and design capacity should not normally be more than 50% of the total quantum of rainfall in the catchment area. Waste wire or spillway will be suitably designed to allow the flow of surplus water based on single day maximum rainfall after the tank is filled to its maximum capacity. The cutoff trench be provided to minimize seepage losses both below and above the nalla bed. To avoid erosion of embankment due to ripple action, stone pitching be provided upstream to the high flow. And the other aspect is monitoring mechanism is benefited as well as catchment area using observation tanks or observation wells, and also some staff gauges can be provided to assess the impact and benefits of the percolation tanks. Now we will discuss about the check dam cement plugs. So check dams, you might have seen in some places, check dams are constructed across the small streams having gentle slope and are feasible both in hard rock as well as the alluvial formations. The site selected for check dam should have sufficient thickness of permeable bed or weathered formation to facilitate the recharge of stored water within short span of time. The water stored in these structures is mostly confined to stream course and the height is normally less than 2 meters. These are designed based on the stream width, and excess water is allowed to flow over the wall. In order to avoid scouring from excess runoff, water cushions are provided at the downstream side. To harness the maximum runoff in the stream, series of such check dams can be constructed to have a recharge in the regional scale. A series of small bunds or wires are made across the selected canal sections such that the flow of surface water in the stream channel is impeded and the water is retained on the pervious soil or the topsoil or the top surface for longer time. And the canal bunds are constructed across bigger canals of second order stream in areas having gentle slope. So what we should consider the site characteristics and also the guidelines for designing. For selecting a site for the check dams, we need to see some few parameters or few conditions. They are like the total catchment of the canal should normally be less than or between 40 to 100 hectares, though the local situations can be guiding factor in this. The rainfall in the catchment should be less than 1000 millimeter per annum. The width of the canal bed should be at least 5 meters and not exceeds 15 meters, and the depth of the bed should not be less than 1 meter. The soil downstream of the bund should not be prone to waterlogging and should have a pH between 6.5 to 8. The lands downstream of check dam should have irrigable land under well irrigation. The canal bunds should be preferably located in area where contour or graded bunding or lands have been carried out. The rock strata exposed in the ponded area should be adequately permeable to cause groundwater recharge through ponded water. The canal bund is generally a small earthen dam with a cut-off core wall of brickwork, though cement bunds or plugs are now prevalent. And for the foundation of core wall, a trench is dug with 0.6 meter wide in the hard rock or 1.2 meters in the soft rock of the impervious nature. A core brick cement wall is erected 0.6 meters wide to stand at least 2.5 meters above the canal bed, and the remaining portion of the trench is backfilled on upstream side by the impervious clay. The core wall is buttressed on both sides by a bund made of local clays, and on the upstream face stone pitching is done. Normally the final dimensions of the canal bund are length would be approximately 10 to 15 meters and the height would be 2 to 3 meters and the width will be 1 to 3 meters. Generally these are constructed in a trapezoidal form. If the bedrock is highly fractured, cement grouting is done to make the foundation leakage free. This is one thing. And you might have seen the gabion structure. This is a kind of check dam being commonly constructed across small streams to conserve the stream flow with particularly no submergence beyond stream course. The boulders locally available are stored in a steel wire. This is put up across the stream's mesh to make it as a small dam by anchoring its stream side. The height of such structure is around 0.5 meters and is normally used in streams with a width of about 10 to 15 meters. The cost is also very less for these kind of structures. The excess water overflow this structure, storing some water to serve as a source of recharge. The slit content of the stream water is in due course is deposited in the interstices of the boulder to make it more impermeable. And next we go for the modification of village tanks as recharge structures. The existing village tanks, which are normally silted and damaged, can be modified to serve as a recharge structure. In general, no cut-off trench and waste wire is provided for village tanks. And when it comes to the inter-watershed transfer, the percolation tanks in a watershed may not have enough catchment discharge, though a high capacity tank is possible as per the site conditions. In such situations, stream from nearby watershed can be diverted with some additional cost and the tank can be made more efficient. The same way we will discuss about the dug well recharge. In the alluvial as well as hard rock areas, there are thousands of dug wells which have either gone dry or the water levels have declined considerably. These dug wells can be used as structures to recharge. The groundwater reservoir, storm water, tank water, canal water can be diverted into these structures to directly recharge the dried aquifer. By doing so, the soil moisture losses during the normal process of artificial recharge are reduced. The recharge water is guided through a pipe to the bottom of the well below the water level to avoid the scoring of bottom and entrapment of air bubbles in the aquifer. The quality of source water, including the silt content, should be such that the quality of the groundwater reservoir is not deteriorated. When it comes to the recharge shaft, these are the most efficient and cost effective structures to recharge the aquifer directly. In the areas where source of water is available either for some time or perennially, example a base flow or springs etc., the recharge shaft can be constructed. And for constructing a recharge shaft, some of the site characteristics and the design guidelines are like to be dug manually of the strata is non-caving nature. If the strata is caving, proper permeable lining in the form of open work, boulder lining should be provided. The diameter of the shaft should normally be more than 2 meters to accommodate more water and to avoid eddies in the well. In the areas where source water is having silt, the shaft should be filled with boulder, wood and sand from bottom to have inverted filler. The most or the uppermost sandy layer has to be removed and cleaned periodically. A filter may be provided before the source water enters the shaft. When water is put into the recharge shaft directly through pipelines, air bubbles are also sucked into the shaft through the pipe, which can choke the aquifer. The injection pipe should therefore be lowered below the water level to avoid this. Now let us discuss about the main advantages of this technique. It does not require any kind of acquisition of large piece of land like percolation tanks. There are practically no loss of water in the form of soil moisture and evaporation, which normally occurs when the source water has to traverse the Vadose zone. And we can disuse or even operation dug wells can be converted into the recharge shaft, which does not involve additional investment for recharge structures. The technology and design of the recharge shaft is simple and can be applied even where base flow is available for a limited period. The recharge is fast and immediately delivers the benefit. In highly permeable formations, the recharge shaft are comparable to percolation tanks with no submergence and hence no land compensation to local farmers. The recharge shaft can be constructed in two different ways, vertical and lateral. So, we will discuss about the vertical recharge shaft first. The vertical recharge shaft can be further improvised with injection wells at the bottom of the shaft. Without the injection well, ideally suited for deep water levels up to 15 meters. The presence of clay is encountered within 15 meters, effective in areas of less vertical natural recharge. Copious water available can be effectively recharged, effective with silt water also. Depth and diameter depending upon the depth of the aquifer and volume of the water to be recharged. The rate of recharge depends on the aquifer material and silt content in the water. The rate of recharge with inverted filter ranges from 7 to 14 liters per second for 2 to 3 meters of diameter. This is about the without injection well. If you are considering a vertical recharge shaft with injection well, in this technique at the bottom of recharge shaft, A injection well of 100 to 150 mm dia is constructed, piercing through the layers of the impermeable horizon to the potential aquifers to be recharged or reached about 3 to 5 meters below the water level. Ideally suitable for very deep water levels more than 15 meters, and these aquifers are overlain by impervious thick clay beds. Injection well can be with or without assembly. The injection well with assembly should have screening in the potential aquifer at least 3 to 5 meters below the water level. The injection well without assembly is filled with gravel to provide the hydraulic conductivity so that the water is directly recharged into the aquifer. The injection well without assembly is very cost effective. Depending upon the volume of water to be injected, number of injection wells can be increased to enhance the recharge rate. The efficiency is very high and the rate of recharge goes up to 15 liters per second at certain places. Now coming to the second part, lateral recharge shaft. These are ideally suited for areas where the permeable sandy horizon is within 3 meters below the ground level and continues up to the water level under unconfined conditions. The copious water available can be easily recharged due to large storage and recharge potentials. Silt water can be easily recharged. 2 to 3 meter wide and 2 to 3 meter deep trenches is excavated, length of which depends on the volume of water to be handled with and without injection wells. This structure has been constructed in various places. Now we will discuss about the artificial recharge through injection wells. Injection wells are structures similar to a tube well, but the purpose of augmenting the groundwater storage of a confined aquifer by pumping in treated surface water under pressure. The injection wells are advantageous when land is scarce. So in this we need to understand few points. First is the pumping rate, then the permeability of the aquifer, distance from stream, natural groundwater gradient, and the type of well. In alluvial areas, injection wells recharging a single aquifer or multi-aquifer can be constructed to normal gravel packed pumping well. An injection pipe with opening against the aquifer to be recharged may be sufficient. However, in case of number of permeable zones separated by the impervious rock, a properly designed injection well with the inlet pipe against each aquifer to be recharged need to be constructed. The injection wells as a means of artificial recharge are comparatively costlier and require specialized techniques of tube well constructed, supported by the operation and the maintenance to protect the recharge well from clogging. Then the next technique, induced recharge. It is an indirect method of artificial recharge involving pumping from aquifer hydraulically connected with surface water. This is to induce the recharge to the groundwater reservoir. When the cone of depression intercepts river recharge boundary, a hydraulic connection gets established with surface sources which starts providing part of the pumpage yield. In such methods, there is actually no artificial buildup of groundwater storage, but only passage of the surface water to the pump through an aquifer. In this sense, it is more a pumpage augmentation rather than artificial recharge measure. If you take a hard rock area, the abundant channels often provide good source for induced recharge. check wire in the stream channel at location upstream of the channel bifurcation can help in high infiltration from surface reservoir to the abandoned channel when heavy pumping is carried out in wells located in the buried channel. The greatest advantage of this method is that under favorable hydrogeological situations, the quality of surface water generally improves due to its path through the aquifer material before it is discharged from the pumping well. For obtaining very large water supplies from riverbeds, lakebed deposits or waterlogged areas, collectors wells are also constructed. The large discharge and lower lift heads make these wells economically even if initial capital cost is high as compared to a tube well. In areas where the phreatic aquifer adjacent to the river is of limited thickness, horizontal wells may be more appropriate than vertical wells. The collector well with horizontal laterals and infiltration galleries can get more induced recharge from the stream. Collector wells constructed in seasonal canal beds. These can be effective as induced recharge structures for short periods only. And for these induced recharge, we have some site characteristics and also some guidelines to design it. So a collector well is a large diameter, something like 4 to 8 meters well, from which laterals are driven or drilled near the bottom at 1 or 2 levels into the permeable strata. The central well is a vertical concrete casing in precast rings sunk into the bottom of the aquifer horizon. The bottom of caisson is sealed by thick concrete plugs. Slotted steel pipes approximately 9 mm thickness, 15 to 50 centimeters in dia, having open area about 15% and a tapered leading are driven literally through portholes at appropriate places in the casing. These successive slotted pipes are welded and driven using specially hydraulic jacks installed at the bottom of the casing. The number of laterals is usually less than 16, thus permitting minimum angle of 22 to 30 degrees between two laterals. The maximum length of lateral reported is 132 meters and the total length of laterals is from 120 to 900 meters depending upon the requirement of the field. The laterals are developed by flushing, and if entrance velocity of the water is kept less than 6 to 9 mm per second, these do not get filled by sands. The effective radius of a collector well is 75 to 85% of the individual lateral length. Now we will discuss about the groundwater dams or the subsurface dikes. These are basically groundwater conservation structures and are effective to provide sustainability to groundwater structures by arresting the subsurface flow. A groundwater dam is a subsurface barrier across the stream which retards the normal groundwater flow of the system and stores water below the groundwater surface to meet the demands during the period of need. The main purpose of groundwater dam is to arrest the flow of groundwater out of the sub-basin and increase the storage within the aquifer. By downing so, the water levels in upstream part of the groundwater dam rises, saturating the otherwise dry part of the aquifer. And these underground dams have few advantages, like since the water is stored within the aquifer, submergence of land can be avoided and land above reservoir can be utilized even after the construction of dam. No evaporation loss from the reservoir takes place, no siltation in the reservoirs takes place. The potential disaster like collapse of dams can be avoided. The aquifer to be replenished is generally one which is already overexploited by a tubular pumpage, and the declining trend of water levels in the aquifer has set in. Because of the confining layers of low permeability, the aquifer cannot get natural replenishment from the surface and needs direct injection through recharge wells. Artificial recharge of aquifers by injection wells is also done in the coastal regions to arrest the ingress of seawater and to combat the problems of land subsidence in areas where confined aquifers are heavily pumped. In alluvial areas, injection well recharging a single aquifer or multiple aquifer can be constructed in a fashion similar to the normal gravel packed pumping well. The only difference is that the cement sealing of the upper section of the well is done in order to prevent the injection pressures from forcing leakage of water through the annular space of the borehole and the well assembly. In hard rock areas, casing and well screen may not be required. An injection pipe with opening against the aquifer to be recharged may be sufficient. However, in case of number of permeable horizons separated by impervious rocks like vascular basalts or cavernous limestones, a properly designed injection well may be constructed with a slotted pipe against the aquifer to be recharged. In practice, the injection rates are limited by the physical characteristics of the aquifer. In the vicinity of the well, the speed of the groundwater flow may increase to the point that the aquifer is eroded, especially if it is made up unconsolidated or semi-consolidated rocks. In confined aquifer, confining layers may fail if too great pressure is created under them. If this occurs, the aquifer will become clogged in the vicinity of the borehole or it may collapse. Now we will discuss about a very common technique in urban areas, the rooftop rainwater harvesting. In urban areas, the rooftop rainwater can be conserved and used for recharge of groundwater. This approach requires connecting the outlet pipes from the rooftop to divert the water to either existing wells or tube wells or bore wells or specially designed wells. The urban housing complexes or the institutional buildings have large roof area and can be utilized for harvesting the rainwater or the harvesting rooftop rainwater to recharge the aquifer in the urban areas.